The topic of this lecture is to show the connection between regular and recognizable languages, and really to prove that they define exactly the same class of languages. And I'm going to start this lecture by recalling you the definition of regular languages, and in fact, to do that, I'm going to recall you the definition of regular expressions. And so regular expressions over some alphabet sigma, they were defined in the following way. On one hand, the empty expression and this A, they are regular expressions for all A in sigma. And then the other thing was, if alpha beta are regular expressions, then also you have alpha plus beta is a regular expression, alpha times beta, and also alpha star. They are also regular expressions. And this was as usual in our structural induction definitions. We were saying these are all. And we were also defining, again by structural induction, the language. So languages associated to regular expressions, and they were defining the class REG of regular languages, and we were saying the language associated to the empty expression is obviously the empty language, and the language associated to letter A is obviously the singleton A for all A in sigma. And then the language associated to alpha plus beta is the language of alpha union the language of beta. And the language of alpha beta is the concatenation of the language of alpha and the language of beta. And the language of alpha star is the iteration of the language of alpha. And the main result I want to prove, this is the so-called Kleene's result, or Kleene's theorem. And simply I can just write it like this. I'm going to prove to you that the set of regular languages is exactly the set of recognizable languages. So all these languages defined by regular expressions, they are exactly the languages defined by finite automata. And it's a profound insight, and it's an interesting result from this point of view. The recognizable languages, they are defined from the point of view of computations. They really tell you something about how an input word is driving a computation, starting in a state and ending somewhere else. And on the other hand, the regular languages, they really tell you something deep about the structure of the language. How do you form that language, starting with just singletons and using just union, concatenation, and star. So what this result is saying is that if you think about running computations, or if you think about the structure of the language, in fact you are talking about the same class, and it's also giving you, this result is giving you a practical way of going from one side to the other. If you have the structure defined, you can define the computing device associated to that. And the other way around, if you have a computing device defining a language, then you have a way to say something about the structure of the language computed by that device. So in that sense, I find this a very interesting and quite deep result connecting two different worlds. The proof as such is not too difficult, but I think it's significant on this conceptual level. And so here is how we prove these results. So again, we want to prove that REG is equal to REC. And I'm going to prove first this inclusion. So if I take a language that's, regular, and I'm going to prove that this is a recognizable language. And because REG is defined through structural induction, then obviously our proofs or claim that L is recognizable, this is also going to go by a structural induction. And the way it goes is like this. Obviously, the induction basis, if L is maybe before that, I just make one more line here. So if I just say that being regular, it means that it's given by the language of some regular expression. And now I can start with my induction basis. So if alpha is the empty set, then this implies that L is the empty language, and obviously that's a recognizable language. And on the other hand, if alpha is just letter A for some A from sigma, that implies that L is the singleton A, and that's obviously a recognizable language as well. And now the point is that if alpha is made of some alpha 1 plus alpha 2, what this means is that your language L, if I have, so this is the induction step, so this was the induction basis, and this is the induction step. So now I'm assuming that alpha is alpha 1 plus alpha 2, and I have that alpha 1 and alpha 2 are regular expressions, and they are in such a way that the language of alpha 1 and the language of alpha 2, they have already been proved to be recognizable languages. So this is the usual induction step. So having this, then the language L, which is the language of alpha, is going to be the language of alpha 1 union the language of alpha 2. And we just proved in the previous lecture that the union of two recognizable languages gives you a recognizable language. So we are done. And very similar, we will have that if alpha is of the form alpha 1 and alpha 2, and we have exactly the same assumption. These are regular expressions, and these languages, they are recognizable. Then L, in this case, the language of alpha is the concatenation of these two languages. And again, the same argument. In the previous lecture, we have shown that the concatenation of two recognizable languages is a recognizable language itself. And finally, the third case is when alpha is of the form alpha 1 star, with alpha 1 just like before, a regular expression, and with the language of alpha 1, a recognizable language. And in this case, we have L to be the language of alpha 1 iterated. And again, we have proved in the previous lecture that the iteration of a recognizable language is a recognizable language. So really, all in all, this claim, this part of the inclusion holds simply because we can argue for the structural induction based on all these closure properties we have proved in the previous lecture. Now, the one that requires more convincing. So again, this is the result we are proving. It's this part of the inclusion, and this is arguably the more difficult one, because you are given a computing device and you want to really calculate the structure of the language computed by that device, and so this is certainly non-trivial. It's not too difficult, but it's certainly not trivial. So here is how it goes. So I'm going to take a language. So let's take a language to be recognizable. And what this means is that there is an automaton. So L is the language of an automaton A. And let's say that A is a deterministic finite automaton. So something of this type, some states Q, and I have my input alphabet, and I have a transition function, some initial state Q or Q0, and some final states. So this is a deterministic automaton giving language L. And let me just enumerate these states of Q. So let's say that they are Q0, Q1, all the way to, say, Qn minus 1. And I would like to define the following language. I'm going to say for any such state, so for any two states Qi, Qj in Q, and any m in between 0 and n, I'm going to define the language. I'm going to denote this by Lij with m here in the exponent. And here is what this means. So these are going to be all the words from sigma star in such a way that if you start in state Qi and you do a computation with input word W, that's going to take you to state Qj, so that justifies this I and j. So you go from state Qi to state Qj using the this input word W. But I'm requiring also something extra, and in this computation, you only use intermediate states. So what I mean by intermediate states, anything that is not Qi or Qj. So intermediate states from Q0, Q1, all the way to Qm minus 1. So again, what this means is that, again, Lij with m here, it means that you're going to take all the words that in your automaton take you from state Qi to Qj, and in your computation, you never use state Qm or anything higher than that. You only use states up to m minus 1. And this looks like a very exotic idea to consider this language, but you are going to see that this solves completely our problem. And I just comment that this is a typical construction for this kind of structural problems, if you like, some sort of flux problems in networks. And you are going to see this in several different places in your more advanced computer science courses, especially in algorithmics courses. And we are going to show, so we will prove by induction on M that all these languages, Lij, M, they are regular. And once we prove this, so once we prove this, And it's really easy to see that we are done because language L is going to be the following sum is going to be a sum with Qj in the final states, and it's going to be the language of all these words that start in Q0 and end in J for all the final states, and you are allowed to use any state you want as intermediate state. So if I put n here, it means that you can use all the states from 0 to n minus 1, which is all there is here. So essentially, by putting n here, I'm saying there is no restriction on which intermediate steps to use. So starting Q0 and then in Qj for all these Qj in F, and all of these are proved regular by proving this induction claim. And so by having a sum of regular expressions or regular languages, this is going to give us a regular language. So we only have to prove by induction on M that this language is regular. And here is how we prove it. So induction hypothesis. We've got to prove that this Lij 0 is regular. And the point here is that by putting this constraint 0, you are essentially saying, you know, I don't want to see any intermediate states because there are no states, you know, with index smaller than 0. So you have got to go directly from state Qi to Qj with no intermediary states. So what I mean by that is that this Lij 0 is really consisting of just letters from sigma in such a way that you go directly from Qi to Qj. And this is certainly true for I different than j. And this language is either a singleton or the empty set, and that's certainly a regular language. Now for I equals j, so if I'm just writing Lii, and I'm not allowed to have any intermediate set, so obviously the empty word is also in this language. But other than that, I'm going to have all these letters that keep me in state Qi. And so again, we have the empty word union with something that is either a singleton or the empty set, and so that's obviously a regular language. So we are fine with the induction hypothesis. And now if I'm assuming, so assume that this language or all these languages are regular for all I and j, so for all the states Qi, Qj from Q. And I'm going to reason now about Lij n plus 1. So really what this means is that you are going from state Qi to state Qj, and you are allowed to use any state up to and including Qm. And one possibility of doing that is that you never use Qm. So really that means that you go with this language. So only up to m minus 1. So that's one way of going from I to j, and that's already captured in this word. So if I'm thinking about this Qi, and I go to Qj, and you only see here states such as Q0, Q1, Qm minus 1. So this is what's captured in here. So that's one way of going. But the other way of going is you do visit Qm. I mean, you are allowed to use to visit Qm sometimes. And I would like to really point out every single time I'm going to Qm. So here is one, and then maybe I go another time, and so I maybe visit this several times, Qm. And then eventually I go to Qj. And because I'm writing all the occurrences of Qm in this computation, so here in between I only have states up to qm minus 1. So everywhere here is just states up to qm minus 1. So what this is really is the language of going from I to m and only using states less than m. So this is L from I to m using just m. And then really this part is about going from m to m using states up to but not including qm. And this is the same thing. You go from m to m and you only use states up to m. And you can do this a number of times. So what I'm saying here is that this is obviously the language LMM and using states up to qm but not including qm. And this is iterated on itself. You can have as many occurrences of this qm as you might want in this computation. And eventually you have got to do this step. So this is about going from m to j, and you are only using states up to but not including qm. So this is LMJM. And so as you can see now, I'm using the assumption, I'm sorry, so this was induction bases here. And so I'm using now the induction hypothesis, which is this one, to conclude that every single component in this expression I deduced in here is a regular language. And we have sums, we have stars, and we have concatenation. So all of these are making up regular expressions. And yeah, that concludes our proof. It just shows that all of these languages of the form LIJM, for any M, they are regular languages. And with this, that concludes our proof. So this was the main result I wanted to show in this video lecture, that regular and recognizable languages are the same. And the deeper and to some extent a more interesting part of this result is the second part that I have on this whiteboard. It really gives you a way of calculating the structure of a language defined by an automaton. However, in practice, if you go about it in this way to calculate the regular expression corresponding to an automaton, this is quite a tedious way of doing it, and the regular expression you get is extremely complicated. But fortunately, there is an easy way or easier way to calculate the regular expression corresponding to an automaton, and we are going to discuss that in our next lecture.